Okay, this ugly picture is my model of the universe, my theory of the universe. Okay, how does this work? Let me start over. Here's the essence of it. Um, the universe was contained for a long time. Um, it was just basically a bunch of very, very, very hot gas bouncing back and forth. But then at some point, that gas became far enough spread out that it could begin to proceed outward in all directions like this. And maybe at this point, the uh, the objects here at the center became planets, stars, what have you. Okay. Um, now, but before that, the universe was actually expanding at the speed of light um, from the origin here. But there were other columns going up their own separate ways. And if I drew that, I would draw like a hyperbola there and draw another one up here with with its own uh, like little segment. So if we're right here, 13.7 billion years after these started spreading out, we could look over and see events. We could like look back into the past and see things out to this wall. This is a wall of hot gas right here. Um, but we would see objects like a galaxy here, a galaxy here, a galaxy here, and all of the stuff in this region would be following Hubble's law. And then when we get to a certain point out here, uh, well, it's not following Hubble's law. And maybe you're even seeing some collisions right in here um, between stuff that came out from the original explosion and stuff from that just kind of opened up um, and started being free at this point. You might see some collisions going on between stuff that opened up here and stuff that opened up here. And this diagram, if I drew it right, it should be essentially Lorentz invariant, which means if I look at it from any particular point of view, um, maybe this particle. Well, you know what? That's an unlucky particle. What things would look like from its perspective is that it came out this way, and then it went this way, and it collided with something going like that. So that particle is not a particularly lucky particle because it went this way and then went this way, and it collided with something that was going like that. So on the other hand, this particle is probably pretty lucky because it's managed to reach an equilibrium so that everything is going nice and going away from it, and it's in the center of the distribution. So it's not entirely Lorentz invariant. Um, for these guys over here that are colliding with each other, maybe it's not entirely Lorentz invariant, but those are that tends to be a region of a lot of supernova activity. Probably you could pick out a region of time where supernova activity is fairly common, or like collisions of stars and stars running through gases and accumulating a lot of mass. And then once they get through that period, then you get things to calm down, and you get the universe as it looks nearby. And so you get Hubble's law out to about there, and then you might get something that looks a little bit more random, and probably Hubble's law. So this is Hubble's law is 1 over 13.7 billion years, giga-years, and then out here, h sub naught is greater than or less than, maybe h naught is equal to 1 over 30 billion years. So, okay, in 2016, I put out a copy of this this video, modeling SN1A data Minkowski style, and I basically took the data from IAUC 6861, which was the high Z supernova search team's data, and I basically modeled it. And what I did was I used their right ascension, declination, magnitude, and Z value to kind of calculate a velocity for a velocity and position from each of the supernova. And then I just kind of assumed that that had been moving away from the origin at a constant speed. And basically, that's what this diagram looks like. It goes in time, it goes like this, and then it starts spreading out at, and maybe it doesn't all come spreading out at once. It may come spreading out here, 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 here. And you'll get a bunch of data that comes out before that. And this is what it looks like. Instead of starting 13.7 billion years ago, it starts at 54 billion years ago. And then it just kind of starts like one of the highest Z supernova comes out first, and then a few more. But they don't come out all at once. It's as though that region was packed in, held together by thermal forces, and then over time, the other supernova come out of this. Anyway, this goes on for a while. I think there may be a clump of them right about the what the Hubble's law would be resemble in this diagram is if all of the red dots came out from the center simultaneously. So somewhere, so see right there, it says 13.7186. Right there is when all of the data, or every galaxy, at this instant, every galaxy should simultaneously leave the origin, according to the Hubble's law. So if I hit play right then, all of the rest of the known galaxies would pop out all at once at that moment, and they would all come out in the same direction. But all of these dots have or basically have a Hubble's constant, or kind of a random Hubble's constant that is smaller than the known Hubble's constant. Okay, now I'm reading Dale Darling's response to a question I asked him a little bit ago. The acceleration I was referring to is the acceleration of the expansion of the universe caused by dark energy as evidenced by the redshift in light from the distant galaxies as per Hubble's law and standard candle measurements. Okay, let's go back to this diagram and talk for a second about Hubble's law exactly. My premise is that if I go from here to here, that's delta t right here, and this is distance. So distance is equal to velocity times delta t, right? And so Hubble's law is velocity equals h naught? No, wait. Velocity equals h naught times d. So essentially, h naught is 1 over delta t. So anything that is coming out of this event here will follow Hubble's law, but anything that comes out before that will use, basically I've been describing it as having a different Hubble's constant. So that's the way this model presents what Hubble's law is. However, using calculus and some kind of clever tricks, they have models where this data that I've been showing you actually fits so that they make that h naught a constant. Okay, so Dale Darling continues, when examining galaxies at opposite ends of the visible universe, cosmological redshift illustrates the velocity change between us and those most distant galaxies, and it is the same in all directions. The velocity change between us and a galaxy at the edge of the universe in one direction is the same as the velocity change between us and a galaxy at the edge of the universe in the opposite direction. So I think what he's saying is we have pretty much symmetry. So the velocity of the object over here is pretty similar to the object over there. They, whether or not they follow Hubble's law, they are symmetrical. So thus they cancel out, and we must exclude velocity change from consideration, meaning we cannot skew the diagram. Now, in Veritasium's video, they skewed the diagram so that they brought one side up and the other side down like that. And I don't know if you can skew the diagram like that or not. The thing is, skewing the diagram, it basically has no effect on whatever is inside it. However you modify it by doing linear operations on it, stretching, skewing, whatever, all of the events that happen in the diagram are still there. So unless you do something that actually changes the readings on dials, the images on your cameras or anything like that, then there's no then it can't affect the physics. The reason that special relativity can change things is because of these things right here, changes in velocity, where this guy goes from stopped to, he changes his concept of what is stopped. When he decides that this line is stopped, that changes his view of the universe. That changes his point of view. So just like this tiny man holding this box, it does nothing to him if I rotate this diagram however I want. He still thinks he's lifting up that tiny box. But if he was outside the picture, he would know that, I mean, if whatever operation I do affects every event in the universe, then he can't tell that anything has happened. But if he But if he turns over and the rest of the universe stays the same shape or stays in the same orientation, then he would notice a difference. That's the same thing with space-time. If I do an operation that just skews time, so over here it goes up all the way, goes forward in time, and this part down in time, then nobody in the universe would know, as long as the operation affected the entire universe equally. But if somebody is in there and changes direction, then he will know, because he can see the effects of what his change in orientation did on the space-time. Okay, um, Dale Darling continues, this leaves us with the original unskewed diagram as per Veritasium's video. In this case, in an asymmetrical speed of light universe, we would see the light from the infinitely fast direction arrive instantly, while the light from the slow direction wouldn't arrive until 2c later, thus showing us a younger galaxy from that direction and an old galaxy from the infinitely fast direction. Does that make sense? What I'm trying to figure out here is whether Dale is talking about this this strange skew that Veritasium did, or if he's actually talking about special relativity, because those are two different situations. Let's draw a little picture. Here's our camera, and this is time going this way. That's the future. This is the past. This is what the camera can see. This is speed of light signal coming to the left towards the camera. This is speed of light signal coming to the right towards the camera. And we have an object moving towards the camera. Let's see. We have an object coming towards the camera. So scene 1. Okay, this is position 1, position 2, position 3, and then I'll just continue position 4, position 5. After it passes him, position 6. Okay, what happens then is that the location where he sees this object is right here. And then the next location where he sees this object is right here. And then the next location is right here. And then the next location's there. Next location's there. Location 5, location 6. Okay, do you see something peculiar about these dots? Over here, 1, 1, 2, 3. This looks like it's coming very, very fast when it's coming towards you. And then 4, 5, 6, it looks like it's going very slow when it's going away. As a matter of fact, turns out there is no limit to the oncoming velocity, the oncoming apparent velocity, because these can get, if these get arbitrarily close to the speed of light, they can end up being really, really, really fast towards the camera. But on the way away, they are limited to 1/2 the speed of light. However, this example had nothing to do with an asymmetrical speed of light. It was just an object that was coming toward you and then going away from you after it passed you. You can actually see some of this if you go to www.spoonfedrelativity.com and click on essays and articles, and then come down to, what is it, Penrose-Terrell rotation.php. It's not very well titled, but it has a lot of cool, or has a bunch of animations that I made some time ago. Coming down, and where's the final one? That's not the last one. There's one that's really cool down here. Is it this one? No, there's more. This is a simulation of a of a ball coming down a fence at 99% of the speed of light, you'll notice that it comes in really, really, really fast and then slows down a whole lot. And that's just from the effect of that I was just describing of with these lines being lined up, coming in fast and then going slow. But with, instead of being at this slope, being at 99% of the speed of light. I actually kind of think it's kind of terrifying that something that is coming at us at 99% of the speed of light would look like it's going almost 100 times the speed of light. But that's just me.